Dear students, let us talk about the number system and their interconvertibility. You can see the table itself. We have got decimal system, we have got hexadecimal system, and we have got binary system. Truly speaking, decimal system is a system where we normally talk from our childhood. Hex decimal number system we need actually to understand and use this binary number system. Here you can clearly see when you talk about decimal, it starts from 0 and goes till 9. Total digits are 10. That's why it is called decimal system. Similarly, when we go in hexadecimal, it starts from 0 and goes till F. You can clearly see till F. And hence it is called hexadecimal system. Total digits are 16, including 0 till F it is 16. And these are the binary equivalent of these numbers. You can clearly see that it is starting with 0, 0, truly speaking 0, 1, and then become 1, 0. So in decimal it become 1, 0 after 9. And in hexadecimal become 1, 0 after F. And here it become 1, 0 immediately after this. After 1, that is 1, 0. So 0 and 1, only 2 bits. So it is binary. In hexadecimal we have got 16. In decimal we have got 9. For example, in hexadecimal, once you reach to F, then 1, 0 will come. Let's move ahead. As far as the weightage is concerned, it's very clear that the number 1111 looks similar, but actually its value is different. For example, when you talk in decimal, it is exactly 10 raised to 3 plus 10 raised to 2 plus 10 raised to 1 plus 10 raised to 0. Actually multiply with 1 everywhere. So it is understood. And it comes out to be nothing but actually 1111. This is the value in decimal. But when you go to hexadecimal, same value is 1 16 raised to 3 plus 1 into 16 raised to 2 plus 1 into 16 raised to 1 plus 1 into 16 raised to 0. When we add these values, we get nothing but 4, 3, 6, 9. Similarly, when you talk about binary, it is 1 into 2 raised to 2 raised to 3 plus 1 into 2 raised to 2 plus 1 into 2 raised to 1 plus 1 into 2 raised to 0. If you calculate it, it comes out about 15. So this is actually 15. So it's very clear that the value 1111 in decimal is equivalent is not same in hexadecimal and not same in binary. The value varies as the base varies. So it is an equivalence. It's very simple that if you are given an arbitrary binary number, for example this, and if you take a combination of 4, 4 from right, then you can clearly see that the digit comes out to be 8. It's E, it's again E, it's 7, it's F, it's A. With the due time you remember the values. For the time you can see your table which is given in the beginning. So this is how we convert binary into hexadecimal. What are the number binary given? Make a combination of 4, 4. Why 4, 4 exactly? The biggest value in hexadecimal is 15, represented by 1111. Hence we make a combination of 4, 4. It's very interesting. If you see very carefully, if I see the binary equivalent of 2, 4, 6 and 8, it's actually 1, 0, 1, 0, 0 and this one. The important thing is all are even numbers and all having 0 in the LSB position. So the conclusion is all the binary numbers having 0 in LSB are actually even numbers. Same way, there is no need to talk when you talk about 1, 3, 5, 7. It's 1 in the LSB position which decides the number is an odd number. For example, arbitrarily given 3, 4, 5, C. Then there's no need to break all the numbers into binary. Just see the last one, 1, 1, 0, 0. And this itself, there is an even number. This is how we find out even and odd. Similarly, when you talk about a negative and positive number, in that case, the most significant bit is reserved for the sign. For example, you are given a number d5, break into binary, just this is reserved for the sign. So number, this 1 is actually given a minus sign, and this number is actually 55. Similarly, for positive numbers, you should have 0 in the beginning. It is very clear that if we are dealing with sign numbers, the size of the number reduced to only 7 bits. It is no more 8-bit number. Now this is something very interesting. If we have to find one's complement of a number, I am taking an arbitrary number DC. If you write a binary form of DC, it is 1, 1, 0, 1, 1, 1, 0, 0. If I make all the zeros and ones as zeros, I get nothing but 1, 1. This is nothing but 23. If I add 1 to this, I get 24. My original number was DC. This is 1's complement and this is 2's complement of DC. The other way of finding 2's complement is, or 1's complement is very simple. The given number you subtract from the largest possible number. You can see this is 15 minus 12, which is nothing but 3. This is 15 minus 13, which is nothing but 2. If I add 1, I get nothing but 24. So the simple way of getting 1's complement and then 2's complement. The interesting thing here is DC, if I add to 2's complement, this is 12 plus 4, that is 16, 16 minus 16, we're in hexadecimal. It is 0, 1 will be carry, 13 plus 1 is 14, plus 2 again 16, this is, if I neglect this carry, then the answer comes out with 0. And we know when a number is added to its negative, then only we get 0. That means in number system or in a binary number system, we don't have a minus sign as it is. DC is negative of 24 and 24 is negative of DC. If I can simply write, I can write DC is nothing but 24 with a minus sign and vice versa. So 2's complement of a number is nothing but its negative number. Now when you go to addition and all, you have to simply remember that when we add a number in decimal, whenever summation is more than 10, then the carry goes. So here 7 plus 5 is 12. 12 is more than 10. We subtract 10, that 10 goes as carry. And you go to 2. 6 plus 4 is 10 plus 1 is 11. Again more than 10. From 11 we subtract 1, it is 1. The carry goes here. 7 plus 5, 12 plus 1 is 15, and this is here. Again 12 plus 1, that is 13. So the thing to remember is whenever the summation is 10 or more than 10, then only the carry goes. Same concept we'll remember in hexadecimal. Whenever the number summation is 16 or more than 16, then only carry will go. So you know 7 plus 5 is 12, in hexadecimal it is C. 6 plus 4 is 10, in hexadecimal it is A. 5 plus 7 again 12, in hexadecimal it is C. By chance none of the summation exceeds more than 16, hence there is no carry. Now subtraction is equally interested. Decimal subtraction is just for understanding here. 7 plus 5 minus 5, 2 is not a big issue for us. But whenever the bigger number is subtracted from the smaller number, like here, then we need to take a borrow. So whenever in a decimal, you have to take 10. So 10 plus 4 is nothing but 14. 14 minus 6 gives me 8. So 1 less here. So it is 8. 8 minus 7 is 1. So it is very simple thing to remember is we need to take borrow. We have to take 10 as borrow. Similarly here, whenever we need a borrow, you have to take 16 as borrow. You can clearly see here 7 is less than 9. I cannot subtract 9 from 7. I have to take carry. 16 plus 7 will be 23. 23 minus 9 is nothing but 14. And hence I am getting a E. Now this was 3. Again 16 plus 3 is 19, 19 minus 9 is nothing but 10, which is represented by A. It becomes 7, 7 minus 4 is nothing but 3. The important thing to remember is whenever you take a borrow, you have to take 16. There is no need to tell after F 1 0 comes. This is 15, this is 16. Though it looks to be we are taking 10, but actually it is nothing but 16. Thank you.